if I'm thinking correctly, this is about where we left off yesterday. Okay, so it's very electronegative, so it's a very strong dipole, but like I just said as we're going over the homework, it's more than just that big electronegativity difference. Those three atoms are tiny. They're small, up in the small corner. And small atoms can get closer together. The closer together they can get, the better they can stick. Just like a magnet, the closer it gets to the metal, the better it pulls. The closer together the atoms can get, the better they stick. So because they're small, they can get close together, which means they call that a big charge density. That the charge is really dense right there, instead of mass density, charge density. Okay. All of those will have lone pair when they're hooked to hydrogen. And lone pair is a couple electrons just sticking up into space. Next to an H, that's really positive. So it hooks on. It hooks on like a temporary bond. It's got that positive H sitting right next to places with lone pair. And the molecule next to it will have the same thing, because you can only do it between these two kinds of molecules. So they'll be able to share with each other's lone pair and hang on really well. This is by far the strongest of the intermolecular forces. But even as the strongest of the intermolecular forces, it's only 5% as strong as a real bond. Okay, this is not a real bond, it's named wrong. It's not a permanent attachment, it's a temporary attraction. Not anywhere near as strong, about 5% as strong. But it plays big roles in how things behave. Okay, so that's the hydrogen bond between water molecules. The lone pair on one molecule is going to be attracted to the positive H on that molecule. But notice that this has another positive. These have some more positives, or this has a negative. So it's really going to be like that. But you're going to have a network of them. And what happens is water can actually make, on average, 2 hydrogen bonds. So water's held together extra special, because not only does it make a hydrogen bond, it can make 2. One off one hydrogen, one off the other hydrogen. So it can make 2. Or one with one lone pair, or one with the other lone pair, depending on which way you look at it, which side you look at it. But on average, they can make 2. So how strong are the molecular forces? Well, in order of increasing strength. Starting with the weakest. The weakest ones are dispersion forces. Because a temporary dipole induced by a temporary dipole next to it, doesn't sound like these charges are around very long, are very big, so they're not going to be able to hold them together very well. Permanent dipoles attract better. Polar molecules stick together better than nonpolar molecules. And then hydrogen bonding. But they're all much less than real bonds. To give you an example, we saw the intermolecular forces. You saw that boiling was tearing those forces apart. Well, it takes about 40 kilojoules to boil water. That means take the water molecules away from each other to do a mole of that. But remember, it took 347 to break one carbon away from one carbon. So much weaker. Okay? Now, dispersion forces get stronger if the molecule has more electrons. So the more electrons the molecule has, the stronger the dispersion forces has. So small molecules stick together less than big molecules. the more polar it is, the stronger the force is going to be. The bigger the partial charges, the more often, the better they're going to stick together. Opposites attract, more opposites attract more. So, which kind of molecules can do each of those types of intermolecular forces? How are you going to decide which intermolecular force it is? Okay. So, dispersion forces. What kind of molecules can do dispersion forces? Well, dispersion forces are caused by the electrons moving around. What kind of molecules have electrons? All of them. So what kind of molecules can do this? All of them. They don't even have to be molecules, they can be atoms. Right? You only notice it with nonpolar molecules, because that's all nonpolar can do. So nonpolar can only do this. Okay. Dipole interaction. Dipole means two poles, so what kind of molecules are going to be able to do dipole interactions? Polar. And then hydrogen bonding. Hydrogen attached to fluorine, oxygen, or nitrogen. Knopf said, backwards. Okay. So, one of the places it shows up, one place the hydrogen bonding shows up, is in some familiar chemicals. Adenine, guanine, cytosine, and thymine. Those the DNA bases, right? Okay, so these are the shapes of the DNA bases. Okay, and they've actually color-coded where the charge is. So the parts that are blue are partially negative, and the parts that are red are partially positive. Okay? Now, in bio class, they taught you that the same ones always went together. So which ones went together? What went together with guanine? Cytosine. Okay? And the reason why guanine and cytosine go together is because that's got a negative area here and a positive area there. And then two negative areas here and two positive areas there. So that if I push them together, the positive and negatives attract each other. Now if I do adenine and thymine, it's got a positive on the bottom and a negative on the bottom, a positive on the top, a negative on the top, and the opposite in the middle. All those regions of charge, all those regions of charge line up so that it's going to attract like this. Now, are those real bonds? No. But the wrong ones won't fit together. Everybody see why those two wouldn't fit together? Okay, so that top right there would be pushed apart. Okay, so you can't put those two together. So they're actually hydrogen bonds. It's just showing electron stuff, but I know that's actually there are hydrogen bonds between these pieces, not showing some H's. Okay. So that means that you can have the bases on separate DNAs, strands of DNA, and they're going to be specific. Only the right base is going to go in there when you try to take it. And you can take it apart because they're not real bonds. They're just intermolecular forces holding those two strands together. So that you can take it apart, read it, and then it'll fit back together the same way. Does that make sense? And if you're trying to copy it, only the right base pair of the other side is going to line up. Right? So that's how, so the specificity of those polar regions is what makes DNA self-assemble. Sense? So that's a pretty big use for it. Okay. I like to look at boiling points to show you the differences, how the different ones affected. So here's the boiling points of group 4s with hydrogen. So all I'm going to do is compare the different groups when they're combined with hydrogen. So group 4A combined with hydrogen. Why? What would explain the fact that the boiling point goes up as I go from C to Sn? Electronegativity? Well, actually, what shape are all of these? They're all tetrahedral, aren't they? So tetrahedral is symmetrical, so it can't be polar. These are all nonpolar. So why would tin with 4 hydrogens have a higher boiling point than what makes nonpolar stronger? More electrons. So this is just this increase here is just the fact that tin has more electrons than carbon. And so there's a lot more electrons can move around more. Make sense? More electrons move around more. Okay. Next, I'm going to do group 5A. Group 5A has 3 hydrogens. They're all going to be trigonal pyramidal because they're going to have 3 hydrogens in a lone pair. And all trigonal pyramidal. Over here, we see a gradual increase. The same as the one down below. That's because of London dispersion forces. They just generally have a higher boiling point the more electrons they have. Because these two have the same number of electrons. And these two have the same number of electrons. So this gradual increase is because of the number of electrons. This part right here, the fact that these two are, let's change the color so you can see it. This part right here, the reason why they're higher now is because trigonal pyramidal is not symmetrical. Every one of these is polar. So these are all go up. That's the difference that polar makes. Polar versus nonpolar. So we still have the gradual increase because of number of electrons. We have a jump up because that much more stick together that much better because they're polar. But something's going on with NH3. Because if NH3 was just polar, you'd expect it to be here. Right? But notice it's way up here. That's about hydrogen bonding. So see, so NH3 is polar, so it's a little bit more. It's the extreme of polar hydrogen bond, and that makes a big difference. See how the boiling points show you those things. Okay. Next, I'm going to do group 7A, the halogens. Group 7A, once again, we have a gradual increase, right? Because they get bigger. Hydrogen iodine has many more electrons than hydrogen chloride or hydrogen fluoride. It's got the increase because it's polar, not quite as polar apparently. And HF, well, if HF was just polar, we'd expect it to be around here. But it's not, because it can hydrogen bond. Question?
So hydrogen, fluorine, hydrogen bond
would be this. Would be a. Well, the more electronegativity difference, the more polar it is, the stronger it is. But something else is going to surprise you on the one I skipped. Okay. I skipped group 6A, the ones that make 2. They make 2, they're going to be bent. They're going to be polar. Once again, we have a jump because they're polar. We have the gradual increase because of more electrons. And we'd expect it to be here. But notice, if it could hydrogen bond, we'd expect it to be here. That's about how big the jump was for the other two, right? But that one goes up again. Because water can hydrogen bond twice. And HF can only hydrogen bond once. Because HF has one hydrogen to hydrogen bond with and 3 lone pairs. So it can only hydrogen bond once with that one hydrogen. H3, or NH3 has 3 hydrogens, so you expect more hydrogen bonds, but it has only one lone pair it can share with. So the lone pair limits you to 1 hydrogen bond. Water has 2 lone pair and 2 hydrogen, so it can hydrogen bond twice, so that hydrogen bonding has a bigger effect for water than it does for hydrogen fluoride or ammonia, NH3. Okay, make sense? So, what type of intermolecular force does HF have? Correct answer is? Does HF have electrons? Yes, it can do London dispersion forces. Is HF polar? Yes, it can do dipole interactions. Does HF have H hooked to N, O, or F? So it can do all 3 of them. That make sense? CCl4. Yesterday we drew it like this. Dots around everything. Okay. The bond between carbon and chlorine was polar. Chlorine was 3.0, carbon was 2.5, so it was a difference of 0.5. That made the chlorines negative and the carbon positive. Okay, which ones can it do? Can this do London dispersion forces? Yes, it has electrons. Can it do dipole interaction? It's got polar bonds, but what shape is it? Tetrahedral, so it's symmetrical, so it's nonpolar. Chlorine's on the outside. Okay? So it can only do London dispersion forces. It doesn't have any hydrogen, so hydrogen bonding's out. NF3. Well, does it have electrons? Yes. N is going to be hooked to 3 Fs. For some reason, it wants to erase everything I write on the left-hand side of the screen. And then you fill in all the dots, make everybody happy. Because what happens is if you don't fill in all the dots, you forget to put that lone pair on top of the nitrogen. Okay. And that lone pair on top of the nitrogen, well, N is 3.0 and fluorine's 4.0. Okay, so it's got an electronegativity difference. The fluorines are negative. N is positive. But so it's got polar bonds. Is it polar? Yeah, because the shape is trigonal pyramidal. All the fluorines are down on the bottom, negative. Nitrogen's up top, positive. If you say if you say the positives, if you could pick a side where the positive is, if the answer positive is on a side, it's polar. Positive's in the middle, it's not. Same for negative. So it can do dipole interactions because it's polar. Can it do hydrogen bonding? No. Okay. Okay. Ooh. Which of those has the highest boiling point? Okay. Type of intermolecular force. Atoms by themselves. Can atoms by themselves be polar? No. So it's it's H2 polar. H and H are going to share perfectly. So it's nonpolar. So all of these are nonpolar. So the highest boiling point would be the one with the most electrons. Krypton. Most electrons. Because if we can only do London dispersion forces, what makes London dispersion forces stronger? More electrons. Biggest atom, biggest number of electrons, going to stick together the best. You can't answer that. That's not fair because you don't have an electronegativity table in front of you. Okay. So that's what I'm going to have you do today is answer those kinds of questions. Okay. So tell me. Yeah. Yes. Yeah. Because I had to switch a couple of days around because I got to reassemble my lab.